Dear students, as I promised, this lecture will be in the online format, and given we skipped one of the lecture during the hurricane because of the hurricane, so I'll do our basic networking review as I promised last time. And in this section, I call it the networking review. I'll try to go over link layer first, and then a little bit of IP layer or like network layer in more details, and we're going to continue next time. So effectively, we already covered that at the network layer, it's about the host-to-host communication, like within a single LAN. And just to give you very, very brief understanding what the link is. So it's effectively is the actual medium, like or communication within the medium, and its adapters. And to give you like a random example of what those adapters are, so it can be like fiber optics, it can be like the air, like magnetic waves, it can be even like the pigeon that we used to have some time ago. And on the opposite side of like the actual medium, there are network adapters. So you probably saw some of these, like at least the traditional network adapters. And I don't know whether anybody seen these PCMCI cards that have been popular for the mobile devices some time ago. And some other, like there are tons of other devices that can actually act as network adapters. So effectively, the role of the network adapters is to adapt communication to the medium. And there are a few functions, very important functions that have been done at the level of the network adapter. So first of all, it receives the packet from the network layer, and it has to encapsulate it in a specific frame. It may create a multiple frames. So for example, as you will see in a wireless case, it's actually creating multiple. Let's see if original frame was packet was big enough, it will issue like CTS, like CTS, RTS, like request to send, and then we'll expect RTS, CTS to come, confirmation for the send. And if only confirmation been received, it will create the actual frame with the packet and send it out and actually wait for acknowledgement. And it may actually repeat the same thing over again if it didn't receive acknowledgement eventually. So that's one part. The second part is extremely important part is byte or bit stuffing, depending on which link layer we're talking about. I may include some additional material about this one, but the fact is on a wire, everything is just zeros and ones. There is no actual frame like boundary. So you have to introduce the concept of the frame boundary on somewhere at the higher level. So whenever we put packet on the wire, everything it just becomes some kind of a signal, and you have to introduce some form of kind of logical boundary. So people like one of the obvious thing that people came up is just designating some sequence or like at least 1 byte or sequence of bytes or like several bits to represent the end and the beginning of some specific frame. But if you do so, now you're facing the fact that if you have the same sequence in actual packet, then you have to deal it in some way. So this is exactly what the bit and byte stuffing are trying to achieve. So if they see that reserved sequence, they do some form of adjustment, kind of adding additional bits into the output signal, output whatever the frame that's being created, and kind of to ensure that in actual payload there is no sequence of the frame boundary. And finally, there is a concept of error checking, and in those cases, it can be done in several different ways. In one case, it's just adding additional stuff to the frame to ensure that the receiving side can check for the error, and if it detects some kind of error within this frame transmission, so for example, it's very useful feature in IP case. And so, or in Wi-Fi case where the packets are being, there's a very high chance there's some kind of an error is happening. So the other type is actually not just error checking, but also error recovery. So sometimes it's referred to as FEC, like FEC. It's just adding additional information to the packet. So in some cases of small errors, the packet, the original packet can be reconstructed. So I already mentioned this reconstruction packet, but obviously there is a byte and byte unstuffing. So you receive the packet, or you receive the frame, you have to remove this extra stuff added. First of all, you have to find the beginning and end of the frame, and then remove unnecessary bits from the packet. So that's kind of the basic function of just putting stuff on a wire. So the second basic function is kind of communicating with the layer 2. In the simplest cases, when we have just a point-to-point connection, there's nothing to do. You just put the wire and you assume the other side received it. But in more complex cases, even like on normal Wi-Fi, you have to do some form of addressing. So you have to, whenever you send stuff, you have to identify where you want this thing to be sent out. For example, it can be identified, like I want to identify that specific host that this frame is supposed to be destined. But that's not the only way we communicate. You also can indicate that I want to receive by everybody in this kind of broadcast medium, or I want to be received by some multicast group. So there's some assumption about that. So effectively, if we're talking about Ethernet, if we're talking about Wi-Fi, so we have the concept of MAC address, so like medium access control address, which is simply representing by these 6 bytes. It's a numerical address. It's within this. Did I calculate correctly? 6. Yes, it's supposed to be 48 bits. So it's just a flat address. It's been assigned by the manufacturer. It has pretty much no meaning beyond that. What they try to achieve is to have this address unique across the world. So whatever the network adapter you bought, like you got the iPhone with whatever already built-in network adapters, all of them supposed to have their own unique MAC addresses. And with the 2 to 48 different combinations, I think we're pretty much okay with the uniqueness of the addresses, but in reality it's not that even important. So the importance is on the same network you should not have 2 devices that have the same MAC addresses. And so, for example, you can easily reuse Ethernet. Okay, that's actually not the case because you still can mix and match. But in any case, in some cases you just don't. I mean, it's not that a big deal. Like you can reuse, like after whatever 20 years, the company can start reusing some addresses, assuming those old adapters no longer exist. And I think there's also a mechanism you can, in some cases, set different MAC address, like in the extreme rare case that there is some kind of a collision. And just one thing that I want to highlight. The address blocks, so from the MAC address, normally you cannot tell anything except that you may be able to get who is the manufacturer. And the reason is because some of the manufacturers have the assigned, I mean, all of them have assigned blocks. I think it's the first 3 numbers, first 3 bytes, or maybe some other one. They simply have the block assigned, and from that you can guess that this device is from that manufacturer, but beyond that there is literally nothing to say about the MAC address. And I already mentioned there's a so-called special broadcast address, and for the Ethernet and Wi-Fi it is represented by this FFFFFFF address. As a small side note, like network adapters can work in 2, this is kind of the kernel, the operating system issue. So normally the devices will try to, like the device driver case level, they try to filter out the packets or frames that are not destined to you, or like destined to your MAC address, or destined to this broadcast address, or like some several multicast MAC addresses. But you can always set the kind of device or the network adapter in so-called promiscuous mode. In this case, you can receive all the packets that have been kind of physically reaching your computer. So this is useful for packet sniffing, like if you use TCP dump or Wireshark, and kind of you can do some kind of analysis. In the age of Ethernet hubs, if you like ever saw those things, like when you send the packet, every single node in the Ethernet actually receiving the packet, and it was effectively can sniff the complete traffic that's happening in the system. In today's environment, when we have very smart switches, very reasonably smart Wi-Fi adapters or access points, you will see mostly traffic destined to you, but you will occasionally see some stuff that not really destined to you. Another case that the MAC layer is trying to take on is the concept of collisions. So this one, again, this is very important for Wi-Fi cases. For Ethernet, it's, at least in today's switched Ethernet, it's no longer that a big deal, and because it's literally switched Ethernet is a point-to-point connection between everything. But for the wireless cases, you still have to kind of deal with the concept of collision. So whenever you send packet, somebody else can send packet at the same time. There are several ways how Wi-Fi's deal with that part. There were like several algorithms developed before. Today it is so-called the CSMA-CS, Carrier Sensing Multiple Access Collision Avoidance. So for the old Ethernet, we had the so-called same CSMA, but /CD. So that stands for collision detection. But again, we don't really have old style Ethernet anymore, so it doesn't really apply here. And just to give you kind of random, not random, but like the historical perspective of what can be done, and in some of this actually built into the Wi-Fi, and normally Wi-Fi actually has multiple modes of operation. So, for example, you can do division of the channel into time, or actually you can also divide by the frequency and allocate the different time slots, different frequency slots to different nodes, either by schedule or by kind of pre-allocating them. So the other one, assuming you didn't pre-allocate those things, it didn't define a specific schedule, so you can now kind of have the concept of taking turns. So when like either some kind of a token, or there's a coordinator like specifically telling you, oh, you now talking, you now talking, you're not talking, and until you do that, you cannot start sending. Or another way that is mostly used in normal Wi-Fi. Again, Wi-Fi uses multiple modes. It's also used coordinator. It's not using the token pass, but there's a coordinator function where the access point is asking you to do stuff. And I think there's also scheduled mode. But the majority of the stuff we do the random access control, where simply kind of wake up, run some specific procedure of sensing the channel, assuming the channel is not busy, and trying to send. And if we detect some form of error, we try to recover from those errors. Okay, so for the switches, okay, so the one thing that is quite interesting for switches and the switch technologies, and similar thing exists in Wi-Fi access points. So they reasonably smart. So they don't really forward every single packet received from one port to all other ports. This happens, as I said, it may happen occasionally, but majority of the traffic don't do that. So for the majority of the traffic, the switches kind of learn where the stations are. So for example, I will show this on the next station, on the next slide. So if a node C is sending some kind of a packet to node B, like assuming it already know the MAC address and trying to send this packet. When the switch was just booted, it wouldn't know anything about that. But as soon as the packet flows from C to B, it will actually learn that, it will not learn where the B is because it doesn't know yet. But it will definitely learn where the C is, because the C, like in the frame, like Ethernet or a Wi-Fi frame, it actually indicated that this packet, the source address in this frame came from this specific port. And so therefore it will remember this fact. And after B reply or A reply or do some kind of communication, now switch will learn all the destinations, and everything will be learned, and it will effectively isolate all the traffic between two different nodes. So what exactly is happening is using this so-called the switching table, and it's very nice dynamic learning using the switches, and the process already illustrated, but just to formally define it. Whenever you receive the packet, whenever the switch receives in Ethernet frame, it looks the destination MAC address and look it up in so-called the switching table. If it sees that MAC address in the switching table, and it also indicates which port needs to be used to forward this packet. Then it will immediately forward just to this port and forget about this packet. If it doesn't know, then it simply forward this packet on all ports that except the one that it received the packet. And again, forget about the packet. And next time it receives some response back, it may kind of learn something. And again, I missed one part. So you receive this packet on a specific port, and you also kind of add an entry or update the entry in this switch table to record that the packet to the source address of this incoming frame needs to be forwarded to that one, to that specific port. And it, as shown on this figure, it can work across multiple switches. So it doesn't work just on a single one. You can connect multiple switches, and it just naturally be aggregated. So in some cases, for example, this port 1 will be naturally selected, or will have an entry of kind of as a port number for multiple hosts in the switching table if there is some kind of active communication. Just a few notes. So the switching tables, because of the nature of the communication, because you can reconnect to different places, or you don't really communicate all the time with everybody, and everybody communicating with everybody. So they try to cheat a little bit. So they, in the cheapest hardware, in the cheapest switches, they have very small amount of memory. So they try to kind of expire the existing switching entries in the switch tables quite frequently. And in more expensive, they have like a larger pool of memory, and they can have larger switching tables. So self-learning, I'll just already illustrated, so you can learn a little bit more on the slides when you look at them directly. And so to get a little bit closer to end of this lecture, so there's a notion of the broadcast domain. So whenever we have just connected different switches, different access points, every single packet, every first packet that's being sent out in the system will always be broadcasted, because there's no way, there's no other indication how this packet needs to be forwarded. Like your packet being received, the switch has no idea what is happening, like where it's supposed to be forwarded. So it forwards everywhere. If it's received by another switch, like a switch number 2, again, if that switch doesn't know where to forward that packet to that destination, it will broadcast again, and so forth and so on. So if we have a very large network with multiple different switches, then we potentially have a problem, because the single transmission of a single packet can use up a lot of resources. And that's kind of okay, I'll ask one of the questions in a few seconds, just to highlight one important problem. In switches, you cannot have this kind of loops. And you need to think a little bit of why exactly we cannot have loops. And in old days, when we have like a dummy hubs and even dummy switches, that was a big problem, because if you accidentally connect 2 cables between 2 switches, now the packet, like, there's just like disaster is happening, like so-called broadcast storms happening. And I mean, you have to deal with something. In today's technology, the switches are smart enough to run a so-called spanning tree protocol, where they kind of thinking like actually pruning the unnecessary links if they detect some kind of loop, or actually they're selecting specific links that cover all the nodes, and just not use the additional links to forward packets. But again, like if I get back to this slide and ask you one question, we're going to be talking about the IP protocol a little bit later. And in those cases, you also don't really want to have loops, but those loops are not as bad as IP. So think about this question. I will not give you the answer right away unless it's already somewhere on the slides. But there's a very, very important reason, important distinction between Ethernet packets and IP packets. And in IP packets, it's bad, but it's not critical. In Ethernet packets, it's extremely critical, because if you have a loop and you don't run the spanning tree protocol, your network gonna explode. But if you that would be effectively your class participation homework. Okay, so what we just covered was the Ethernet part. Like, you already learned that the switches can be reasonably smart enough. They can learn like where things are located, but we're not using it on the internet. And kind of the question I put here, and I was like hoping to ask you in class, why exactly we don't really build the whole internet using just Ethernet. But unfortunately, I will have to give you the answer right away. So we're not going to build it. Like, it's not going to be possible. We're not going to build this on the internet. And there are multiple reasons that you already see on the slide. So one of them is really, really inefficient. I just mentioned, if we have a single broadcast domain, a single transmission of this first packet that before every communication can start have to broadcast everywhere. So this is complete disaster if we're talking about on the internet scale. The second one is this forwarding tables. So what we had so far, like what we saw in there, was for every single host there is an entry. I mean, it's dynamically created, dynamically updated, like a pruned at some places, but it's still for every single host. So if you consider how many different hosts, like internet routers, send traffic to, then their routing table, whatever the switching tables, would completely, like, simply explode. And like the performance part is you cannot really do like load balancing. You cannot make use of multiple links because of the problem of looping. Okay, so now we're moving to review of the networking layer, and so this time I'll just I think I'll only cover a few items, just a basic introduction, and a little bit more advanced introduction I will try to cover next lecture. So first of all, talking about the addressing scheme. So for the IPv4, as it was designed originally, there was a different notion of addressing. So we didn't have so-called the classless addressing. So all IPv4 addresses were split into like several classes, A, B, C, and D. And depending on which class you're talking about, they had a completely different interpretation, what is the network and the host ID. But we no longer have this notion. We have switched to the so-called classless addressing long time ago. But the concept is similar. It's just it's more explicit in terms of which part is what. And effectively, all addresses have IPv4, IPv6 have two parts. So one part is this network ID, and the other part is actually the whole thing is the host ID. And I gave you a few examples for IPv4 and IPv6 address. And as you can see, there's this magical /24/64. So I'll cover a little bit more about this in the next lecture. Or you already, like some of you are networking experts, already know how to deal with those things. And for those who don't, you will learn quite quickly. It's a very simple concept. But effectively, some part of the address, like if you're thinking about bitwise representation, is network, and some part of is the host on that network, or just identify the whole thing. And to give you kind of more interesting example, I just converted, I think it's 139.94, 130, and 238 to binary representation, which simply highlights that this part up to some specific point identifies the network, and the rest identifies the rest. The reason I highlighted these boundaries is because of this concept of classless thing. In classless addressing, you're not restricted to have this network to be boundary of in any specific place. So 24 effectively means that the 24 first bits represent the network. Or you can have 23, you can have 25, you can have in IPv4 even 32. Like this will simply represent one address. Or you can have 0 to represent completely all addresses. So for example, there's like so-called default route, which is represented as 0000/0. I think I give you too many zeros. But in any case, it simply represents all addresses in universe. And in IPv6, it's exactly the same. It's just written in a slightly different way. So as a kind of the conceptual IP router is quite simple. So it's very similar, kind of the conceptually it's very similar to the switch, with exception it has a slightly different logic. Instead of just working with Ethernet packets and just forwarding them to different ports, it's actually processing them. It's taking the packet from the Ethernet, extracting the IP part, doing some processing of what needs to be done with this packet, and potentially creates a new Ethernet frame, new Wi-Fi frame, new FDDI frame for if we send in somewhere over the fiber link or some other type of the frame. So it doesn't kind of not restricted on the same technology. And plus the switching fabric and processor can do additional things like running the routing protocols and do some various other magic. The configuration, so I'm actually thinking to get some simple homework or like some exercise for you to configure. So I gave you a random example of configuring links and some basic, what I'm configuring here. Yeah, just interfaces. I'm not even configuring routes here. Yeah, just interfaces on a Cisco router. Each implementation, like I think Juniper would have their own interfaces. On Linux, there's multiple ways how you can configure things on Linux. And there are some helpers, like for example in Google Cloud, if you already played with them, there is this kind of another set of things that you can do in Google Cloud. But just a small illustration. Routing table in IP router is very much similar to routing table in switches, in switch table in switches, with one kind of big difference. So instead of having MAC addresses as a destination, it uses so-called destination prefix. So the kind of one key difference between switch tables and routing tables, in the routing table you don't have to identify any specific host. You can, you're free to do so, but it's not efficient. So for the efficiency purposes, we can actually use the whole network to identify where to forward packets if we receive a packet destined to some of the addresses in a specific network. And there is additional logic of how to figure out which entry to pick, because you potentially have the specific route and you may have like a less specific route, like bigger network, and default route to represent everything. I will try to cover this part in a little bit more detail on the next lecture. But for now, you just remember there is a so-called routing table. Sometimes I use word forwarding table that identifies which network to pick and what destination to use. There is also additional complication here with IP. It's not necessarily enough to identify the interface. So like for the switch, you just identify, oh, you need to forward this packet to this port and be done with this. In IP case, you actually have to identify depending on what kind of forwarding you're doing. So if you're directly connected to the Ethernet, and the host that you're sending is directly connected, then that would be enough. So you identify the host, the interface that you want to send it, and that's it, because that would be directly attached. But if you're sending packets through the router, you need to identify IP address of that router. Otherwise, your computer wouldn't know what to do with the packet. Like, yes, there's an interface, but there's potentially tons of nodes connected to that interface, and you can broadcast. But then, how would you indicate that the packet needs to be forwarded versus it just being broadcast? So you need additional stuff. Again, that would be my question to you during the lecture. So can we use the simple self-learning switching to build the routing table? Give you a few seconds to think about this, because the answer is not that actually simple. And depending on the network size we're talking about, it can go either way. Okay, so I already gave you the answer. So kind of I authoritatively put the answer no in this case, but the answer is maybe. So if you're talking about some small wireless networks, or not wireless networks, like small, reasonably sized networks, you can run some form of discovery where you like broadcast when you don't know what to do, and this packet being forwarded or multicasted everywhere, and you learn eventually how things are getting back. So there are some algorithms for that. They're not that popular because there are easier ways to deal with. And kind of if you going beyond very small networks, then you get in trouble. So like there's a huge broadcast cost, and you have to deal with that. So normally we don't do that. Like there are cases when we do, but normally no. Okay, another question. I like asking questions. So broadcasting on different layers. On layer 2, you again, like you can broadcast. It's not really good to do that because you're still using a lot of resources, and that's why people trying to constrain layer 2 networks to be reasonably small sized, or at least have a ability to constrain them. But the basic operational layer 2, we do initial broadcast. On layer 3, because the network size is extremely huge, then we don't really want to broadcast. But again, there's more complications to that because we have so-called multicast protocols. And in those cases, we want to deliver a single packet to multiple nodes somewhere outside. But even in those cases, you actually need to subscribe. And multicast is not fully working on the internet today, but as it was designed, you actually have to subscribe to a specific multicast group, and only then you would start receiving some packets destined to that multicast group. Otherwise, resource is not going to be wasted. So I want to talk about the building routing table. So I just mentioned that we don't really use this self-learning technology, but rather we use in most cases, we use some form of a proactive routing. So there are some reactive routing protocols as well, but kind of our traditional ones are proactive. So we either proactively set up the static routes, and those we can do manually on every computer, or we receive them from a DHCP server that after we connect it to the network, and we receive some the just default route, but we can also receive multiple different routes. Or we're actually explicitly running some form of a routing protocol, be it RIP that nobody uses anymore, ISIS or SPF, or even BGP protocol to actually exchange who are present in the network, what kind of prefixes or kind of IP addresses available here and there, and then based on that information, based on the kind of collected topology information, routers build the routing table. Again, there are two major algorithms. I don't think, I have a coverage of these. So the two major algorithms, and actually there's a slight combination of these two in BGP, or actually slightly different algorithm. So there's one is a distance vector, and the other one is link state. What I want you to remember from kind of this knowledge. So for the distance vector or path vector, each individual node does not know anything about the overall topology. So the only thing it knows about is what is the cost to send to the destination, to a specific destination using the specific next hop. So if you have two neighbors, you will know what is like the cost is 1 to send to each individual neighbor, and whatever other costs associated to send through that neighbor to some other host nearby. And effectively what they try to exchange this individual information, and eventually they build up the routing tables because they run this process iteratively, picking up the shortest or smallest cost to go to the destinations, and effectively build one. Okay, I'm thinking out loud. You can kind of comment me a little bit more. Or maybe we'll do some simple exercise of with the RIP and OSPF, maybe even BGP, to actually for you to remember a little bit more how exactly they operate. And for the link state and ISIS protocol, it's not ISIS, but it's ISIS. They kind of operate in a different mode. What they're trying to do is to discover the topology and exchange this topology information between all other nodes. And the second part is just to exchange from which node which prefix is being announced. And as soon as every node collected that database of information, it simply calculates a routing table using, I think, a Dijkstra algorithm. And that's it. Path vector is very similar to a RIP protocol in principle, but instead of operating on the number, RIP just knows the cost, like the number 1, number 2, number 3, number 16, which is the maximum in the RIP case. BGP operates on the ES path. So instead of just number, it's to have literally pass ES1, ES2, ES1, ES2, ES3, ES2, ES1, 3, and 4, and so forth. I will try to give you additional examples later. Right now, we're just trying to highlight what what things exist. Before I go further, I want to note to make a note of one small thing. A single prefix, if you're talking about the BGP, so for the RIP on OSPF, maybe the same thing, but it's specifically important for us in BGP case because this is even includes some elements of management. The same prefix technically can be announced in different places. So it doesn't have to be like if you own some prefix /1100/16, you don't have to announce it from a single place in universe, of Earth at least. You can technically have different routers, different networks announcing it in different places. And people doing it, it has implication. And the implication is because the whole logic inside the routing, and BGP specifically, is to pick the shortest route, like shortest path. So now if you announce in three different places, depending on where are you physically, or like in topological sense, the packets that you send in this to 1/1/whatever destination will be forwarded either to one data center or whatever destination, the other destination, or third destination. So in some cases, it would be completely undesirable, like if you have like very unique office and that you're working on there and somehow sometimes when you try to communicate, you're receiving packets back, but sometimes your packets going completely different direction. So that's undesirable behavior. But then there are desirable behavior. For example, in like if we're talking about the DNS servers, so like very some kind of CDN servers, where we actually want the clients to be connected to the closest data center. So in those cases, they actually make use of this technology and they call it Anycast. And in those cases, effectively, when we send packet, the packet will go to the closest destination, closest network that announced that specific prefix. I mentioned word CDNs. I'll talk about them a little bit later. And they, in reality, they use multiple technologies. So they use BGP primarily. With the DNS, they're using Anycast. And in some cases, but maybe not majority of the cases, they use Anycast for the actual HTTP traffic forwarding. So now that would be the last part of this lecture, but kind of important part of the lecture, and it may be confusing for the people who learn in the networking just from this few lectures that I'm giving you, but you have to have a very good understanding what exactly is happening. So let me kind of reiterate what was happening at the Ethernet level. At the Ethernet level, kind of we got the frame or the node preparing the frame. In that frame, it indicates to which Ethernet station this packet needs to be received, and the packet being received by the switch simply processes the frame, looks at the two addresses, and forwards this packet either broadcasting to everywhere or forwarding to a specific port. At the IP layer, when we talked about, I didn't mention a single time MAC address. So everything is done at the IP levels. So when we're looking at the kind of generating IP packet, we're setting up the destination IP address. When we're trying to forward, like we receive the packet as a router, and we're looking up the kind of this destination IP address against the routing table. Routing table indicate which IP address, or like which interface, which interface is for just forwarding towards that, if the host is within that network, or the address of the gateway, IP address of the gateway, if we're forwarding somewhere farther than that. So the problem now, because we cannot send that IP packet in Ethernet. Like it's literally impossible, because we need to create the Ethernet frame, we need to have Ethernet address, but we only have the IP address. So kind of the problem, like what exactly we should do and what IP is doing. I give you a few seconds to think about like what can be done. And I don't know if you have any specific suggestions before you continue this lecture, please let me know. But again, I cannot really stop and ask you questions before that. So there's a solution for that that was invented for IP and for IPv4, IPv6, and it's so-called Address Resolution Protocol. And when I was talking about the TCP/IP model, that was kind of the case when I wasn't quite sure where exactly to put this protocol, whether it's a network layer protocol, where it's application, where it's, I mean, it's not transport, it's not really network layer protocol, it's not really Ethernet protocol, but it's something that covers those things, like at least in part of this. So what exactly is happening kind of when we're trying to merge IP in Ethernet is whenever the IP router needs to send a packet on the Ethernet interface, and it doesn't know, I mean, it doesn't know by definition what MAC address is supposed to be used, it actually queues this packet. It stops all the processing, and it starts ERP protocol. ERP protocol has its own effectively table that has IP to MAC address mapping, and if like initially that table is simply empty, and if the kind of no entry for that specific IP address, then the ERP protocol needs to send a request, and it's simply sending its request to broadcast address, to this FFFFFF, and simply asking in the body of the ERP request what is the MAC address for that IP, for that specific IP address. And if you kind of run TCP dump or Wireshark and try to start communicating, try to ping some host on the internet or on your local network, you most likely will see a bunch of those, like what is the MAC address for this, or what is MAC address for that, what is MAC address for this. And as soon as you get some response back, then you get packet from the queue or multiple packets from the queue, because by the time you got the response, you may already received like hundreds of the packets. And then you start sending them to kind of creating the Ethernet frames with the destination MAC address that ERP protocol told you to do, and then sending those frames forward. So I try to kind of highlight in the text what exactly is happening. I'm not going to go over this line by line. Maybe we'll do some additional exercise during the actual class. But try to take a piece of paper and a pen and create a very simple topology, like the one that I was showing you before. And I kind of go over this example. Because I will be asking, like I'm promising you, I will be asking this question during the exam, like not exactly the same wordings, not exactly the same example, but I will ask you some specifics about how do you merge IP and Ethernet. Okay, so so that was it. What I wanted to talk about, kind of networking review this time. As I said, I didn't cover too much about the IP addresses and IP address calculations and how a routing table operates. I'll try to do it next time. I think it deserves more time than kind of we already spent enough time on other things. And I hope that was kind of you learn something, even though some of you are already network experts. But I hope for those who did know about the networking, did know about these details, I hope you at least got something. If you kind of don't understand something what I was saying, please let me know. Like you can either email me on Slack or ask me in person. Okay, so thank you, and hope to see you in class soon.